Welcome back to G Fun Facts Online. Today, we are not just talking about a faster computer, we are talking about a fundamental shift in the physics of information processing. If you follow technology news, you know that on February 19, 2025, the world of quantum computing changed. For the last 20 years, we have been watching a race between giants like Google, IBM, and various startups, all building massive, golden chandelier-like machines to house quantum processors. They have been fighting a brutal war against something called noise. But while everyone else was trying to build bigger shields to block out the noise, Microsoft was quietly spending 2 decades trying to build a completely different type of particle that simply ignores it. They call it Majorana 1. This is the story of the topological processor, the most significant gamble in the history of computing hardware, and why it might finally be the transistor moment for the quantum age. Let's start by understanding the problem that Majorana 1 solves, because without this context, the breakthrough doesn't make sense. In traditional computing, the bit is your currency. It is a 0 or a 1, represented by a switch that is either off or on. It is robust. You can shake your laptop, heat it up, or drop it, and that 0 stays a 0. But in quantum computing, we use qubits. A qubit isn't a switch. It is more like a coin spinning on a table. It can be heads, tails, or a blur of both, which we call superposition. This superposition is where the magic happens, allowing quantum computers to explore massive computational spaces simultaneously. However, there is a catch. The moment a breeze blows, or the table shakes even microscopically, the coin falls over. In physics terms, this is called decoherence. Thermal heat, electromagnetic waves, or even a stray cosmic ray can cause a standard qubit to crash, ruining the calculation. This is why current quantum computers are kept at temperatures colder than deep space. They are terrified of the environment. The error rates are currently around 1 in 1,000. Imagine if your calculator got every 1,000th math problem wrong. You wouldn't trust it to launch a rocket or design a drug. To fix this, engineers have to bundle thousands of physical qubits together just to act as one single, logical, error-corrected qubit. It is inefficient and hard to scale. Enter Microsoft and the concept of topological quantum computing. This approach doesn't try to build a better wall against the wind. It changes the shape of the coin so that it physically cannot fall over. This relies on a branch of mathematics called topology, which studies properties that don't change even when you stretch or twist an object. The classic example is that a coffee mug and a donut are topologically the same because they both have exactly one hole. You can reshape the clay of a donut into a mug without cutting or tearing it. Microsoft applied this logic to electrons. The Majorana 1 processor is built on the hunt for a specific quasi-particle called the Majorana Zero Mode, or MZM. First predicted by Italian physicist Ettore Majorana in 1937, this particle has a mind-bending property. It is its own antiparticle, but for computing, its most important trait is how it stores information. In a standard qubit, information is local. It sits on one atom or one loop of wire. If you poke that atom, you lose the data. In the Majorana system, the information is non-local. It is delocalized across a pair of Majorana particles separated by a distance. The best analogy for this is a shoelace. Imagine you want to store a bit of information, a 0 or a 1, encoded as a knot in a shoelace. If you look at just one end of the shoelace, you cannot tell if there is a knot in the middle. The information, the knot, is a property of the whole lace, not the tips. Now, imagine a fly lands on the left tip of the shoelace. That is local noise. Does the fly landing on the tip untie the knot in the middle? No. To untie the knot, the noise would have to interact with both ends of the shoelace simultaneously, and in a perfectly coordinated way to unravel it. In the quantum world, that is statistically almost impossible. This gives the Majorana qubit an inherent protection mechanism. The hardware itself corrects errors before they happen. Microsoft projects this could reduce error rates from 1 in 1,000 to 1 in a trillion. That is not an improvement. That is a new species of machine. So what does this machine actually look like? This brings us to the hardware breakthrough of February 2025. The Majorana 1 isn't made of silicon. It is made of a new material class called a topoconductor. This material does not exist in nature. It has to be grown, atom by atom, in a vacuum. Microsoft's Station Q and its satellite labs figured out how to combine a semiconductor, specifically indium arsenide, with a superconductor, aluminum. When you cool this hybrid material to millikelvin temperatures and apply a precise magnetic field, something strange happens at the interface. The electrons in the material sort of split apart into these Majorana Zero Modes at the ends of the nanowires. This creates the protected environment we need. The architecture on the chip is distinct. If you look at a Google Sycamore chip, you see a grid of crosses. The Majorana 1 uses a unit cell called a tetron. Picture the letter H. The 2 vertical lines of the H are the nanowires hosting the Majorana particles. The horizontal bar connects them. A single logical qubit is encoded using 4 of these Majorana Zero Modes located at the tips of that H shape. The beauty of this tetron design is scalability. Because the protection comes from the physics of the material, not from massive redundancy, the qubits can be tiny. Microsoft claims they can fit 1 million of these qubits on a chip the size of a credit card. Compare that to the current roadmap for other quantum computers, which would essentially require a building the size of a football stadium to house 1 million qubits. But having the particle is only half the battle. You have to control it. And this is where the story gets really interesting, and where the recent Nature paper changes the game. For years, the theory was that to compute with Majoranas, you had to physically move them around each other. This process is called braiding. Think of it like plaiting hair. The history of how the particles move around each other records the calculation. If you braid them one way, you get a result. Braid them another, you get a different result. The problem is, physically dragging quasi-particles around a chip with magnetic tweezers is incredibly slow, difficult, and prone to heating up the system. The breakthrough in Majorana 1 is that they stopped trying to move the particles. Instead, they switched to something called measurement-based topological quantum computing. They achieve the braiding virtually. The chip uses digital voltage pulses to couple and decouple tiny sensors known as quantum dots to the nanowires. By measuring the parity, essentially asking if the number of electrons is even or odd of adjacent pairs of Majoranas in a specific sequence, they can teleport the information from one spot to another. It creates the mathematical equivalent of braiding, without the particles ever leaving their seats. This is a massive deal because it turns a hard physics problem, moving matter, into a digital control problem, turning switches on and off. It means the quantum processor can be controlled by standard digital electronics. It simplifies the wiring, the cooling, and the software stack. It makes the device look a lot less like a science experiment and a lot more like a computer chip. Now we need to be realistic. This sounds perfect, but is it working? Microsoft has outlined a 3-step roadmap, and right now we are at level 1. The current Majorana 1 chip has 8 qubits. It has proven the physics. It has demonstrated the ability to create the Majorana Zero Modes and perform the critical parity measurements needed for logic. This is the Kitty Hawk moment. It flies, but you aren't crossing the Atlantic in it yet. The next step, level 2, is resilient. They plan to connect these tetron units into a 4x2 array to demonstrate that as they make the system larger, the error rate actually goes down. That is the smoking gun for topological protection. Level 3 is scale. Reaching that vision of 1 million qubits solving problems in chemistry and materials science that would take a classical computer the age of the universe to crack. We also have to address the skepticism. The field of Majorana physics has a rocky history. There have been high-profile retractions of papers in the past, including some by Microsoft researchers in 2021, where signals thought to be Majoranas turned out to be mundane noise. The scientific community is cautiously optimistic this time, because the data is different. The peer-reviewed confirmation of the topological gap, the energy barrier that protects the qubit, and the successful parity measurements are much stronger evidence than we have ever seen before. However, we are not running Python code on this chip yet. It is a processor in the sense that it processes quantum states, but it is not a general-purpose computer ready for users today. Despite the caution, the implication of Majorana 1 is profound. While the rest of the industry raced to build more qubits, Microsoft spent 20 years trying to build better ones. If this technology scales as predicted, it solves the 2 biggest bottlenecks of quantum computing simultaneously: size and error. It offers a future where we can design new catalysts for carbon capture, new batteries for energy storage, and life-saving drugs, all on a machine that fits in a server rack rather than a warehouse. The age of the topological processor has arrived. The noise is finally quieting down. And for the first time, we can see a clear path from the strange physics of the 1930s to the supercomputers of the 2030s. That is the story of Majorana 1. Thanks for listening to G Fun Facts Online, and we will see you in the next deep dive.